Okay, you should have it now.
I don't.
It's all right. It's all right. We've started and you are the host.
Great. Okay. Good. So we're live. Thank you. My name's Phil Chatterton. Welcome to this Revision Village seminar on water potential. And the way it's going to work today is that we're going to have some lecture style content, and then there'll be some questions thrown in here and there to assess really how you're getting on with your understanding. It's not just me. I've got a colleague behind the scenes, a teacher colleague, who's going to be able to answer some of your questions as we go through. So you can use the Zoom question and answer function for that. So have the Q&A box open for that. The webinar chat is available too, and I'll be checking on that from time to time. But if you have a particular query about that you don't understand some of the content, then put your question into the Q&A so that my colleague will be able to put an answer in directly to your question. Just on the webinar chat, just so I know where everyone is, could you just let me know roughly where you are located, where in the world you are. I'm talking to you from the UK, from North Yorkshire in the UK. I'm seeing answers here from India, Vietnam, Kenya, Finland, Croatia, Sweden, Singapore, all different time zones. So it's a very good morning, afternoon, or evening to you, wherever you are based. It's nice to have you all here. Hope you find it useful. So a bit about me. I've been working for Revision Village, writing some of the revision content for a couple of years, and before that I worked in other online platforms as well as teaching in schools for a long time. And so biology is something I really love, and I love to teach it, and hopefully you'll get some good output from it today. Okay, let's dive in. So we have a couple of QR codes for you to use. This is for a Google sheet, a Google form, should I say, response form for you to record some of your answers to. There might be some multi-choice questions or some structured questions that require a longer answer, and you can use that Google form for that. Please scan that link, and it'll take you straight to it. So we've asked what country you are. Again, using the webinar chat. Just if you would, just give me a brief score, 1 to 10, about your current level of understanding of water potential and what it is. So basically, anywhere low numbers means that you don't really understand it or you've not covered it yet. I hope that's not the case for most of you. The middle numbers, 5, etc., would be you've studied the topic, but there are some concepts or some gaps and things that you want to put right. And a high score like 10 would be that you know the topic well and that you are just looking for some of a refresher prior to your sort of exams coming along. So yeah, let's have a look. So we're getting middling to high scores, which is good, and I think that's a good place for you guys to be in right now, in the sense that a lot of questions on this topic, the examiners see that students have a partial understanding of the topic, but they just need an extra conceptual understanding just to nibble those marks up towards full marks. And I've got some questions for you today that are specifically designed to help you go from those middle level grades up to the higher level grades. I'm glad to see there aren't many low scores, sort of below 4 here, which is great. That would be more difficult, but yeah, good. Thank you for that. Okay, just going back to the PowerPoint then. Okay, let's make a start. So we start with, what is water potential? Water potential is a scary term, and I'm going to start it from the point of view of the term potential. Water potential is a type of potential energy. Now, where you've come across potential energy before in your science education is probably to do with gravitational potential energy in the physics classroom. The sort of potential energy that is converted into kinetic energy in the way that the apple when its stalk degraded, it fell off the tree and hit Isaac Newton on the head. The potential energy was converted into movement. Now, we're not doing a physics session today, but there is a parallel there because water potential, differences in water potential do cause the movement of water. And in putting this presentation together, I wanted to give you a solid definition of what water potential actually is, because it's an important concept in all of life. Water can move by diffusion, as you've learned in your lessons about diffusion, osmosis, etc. But it can also move by differences in pressure. Water is a liquid at room temperature. It's not compressible. So if you put it under pressure, it's going to want to go somewhere, like out of the end of this fireman's pipe. There's also gravity and surface tension that can cause water movement, which are hopefully concepts you're familiar with, but the IB standard level restricts your requirement to know about water potential to solute effects and pressure effects. So we're going to restrict ourselves to that today. It's not easy to measure energy directly in the cells. So water potential is measured in a different way, in the sense that pressure is caused by the movement of materials, fluids from one place to another. Water is no exception. And so thinking back to physics again, and here's the second appearance in this presentation from Isaac Newton, newtons per square meter, or pascals, is a unit of pressure, and it's also the unit of water potential that we commonly use in discussing solute potentials and pressure potentials in living organisms. Why is water potential so important? Well, every single organism, from the smallest single-celled protozoan right through to the most sophisticated, complex eukaryotic multicellular organisms, have to move water around. You know, if you're a single-celled protozoan, you're absorbing water all the time by osmosis from the outside. Presumably, you've got solutes within your cell, and so there has to be some way of getting rid of that water, and that might be a contractile vacuole, for example, to pump the water out, a way of moving water using pressure, right through to sophisticated multicellular organisms like a tree, which has a complex transpiration stream. There are different routes that water can flow through the root system, whether it goes through cells or around cells. And all of that water potential is fundamental to life. It's so important. And I'm going to try today to kind of pick it apart a little bit for you so you can understand the components that make up water potential, that cause water to move where we want it to, or where we don't want it to, or to not move where we don't want it to. Okay. Here's your definition. If you want to write anything down, it will be this: the tendency of water to move into another area. Okay. In the sense that, you know, the apple falling from the tree has got a tendency to move down if the supporting stalk holding it to the tree breaks. And water potential is essentially the tendency of water to move into another area by different means. Now, if there are two areas of pure water adjoining each other, maybe separated by a membrane, and the pressure is the same on either side, well, you could quite confidently predict that nothing's going to happen, because the water will move across the membrane in one direction in the same number of molecules of water moving from one side to the other as going the opposite direction in a given time. Anywhere there's a solute, though, a solute being anything that's dissolved in water, and we'll talk about solvation a bit later. Anywhere there's a solute will be a negative water potential, in the sense that water is going to move away from the area of pure water, not towards it. Okay, so harking back to your lessons that you may have had on, there's a whole subtopic on water, but there's also subtopics on osmosis as well, which I won't dwell on too much today. But of course, this topic and this concept is very synoptic because it relies on your knowledge of water. And we'll put some reminders in today about that. So yeah, water is going to move away from an area of pure water. So we'll end up with a negative pressure in that cell, won't we? Because water is going to be moving from the pure water, not going to the pure water, going away from it. So thinking back to your lessons on osmosis, so the water potential is the tendency of water to move into another area. That's a sort of headline definition. Doesn't help us much when we're trying to consider different cells and so on, but hopefully that'll become a bit clearer throughout today. Okay, moving on. The components of water potential then. There are two components of water potential that the IB requires us to have a knowledge of. And one is solute water potential and the other is pressure potential. And we'll deal with each of these in turn. They're given the symbol psi, and the psi subscript S means solute, and psi subscript P means pressure water potential. So solute water potential is a function of the concentration of solutes in a solution. So there's lots of sol words here. You've got solvents, solutes, solvents, solutions. You might remember that from chemistry or not remember it from chemistry. So it's important that we talk about the solute being the ion or the soluble material that is dissolved in water. Okay. So the concentration of a solute, if you spoon salt into water, the concentration of the salt in that water is going to increase all the time. And so the solute water potential is going to actually decrease all the time for reasons that we'll discuss. Pressure potential is the tendency of high pressure to push water about. It sounds a bit crude, but essentially areas of high pressure, if there's an outlet for that pressure, water is going to move through that outlet. Okay, think about, for example, the buccal cavity of a fish. When a fish breathes, it exerts pressure on the water in its mouth by raising the bottom of its mouth, and that pressure change causes water to be ejected through the gills and to cover the to exchange oxygen with its gill lamellae. Okay, so pressure is employed by organisms to maintain cellular conditions or even the conditions of water levels, etc. These are the terms that are specified in the IB specification: hypertonic, hypotonic, and isotonic. Hyper means stronger than, hypertonic means stronger than in terms of the solute concentration. Hypotonic means less concentrated in terms of solute, and isotonic means the same. Hopefully you're okay with those terms. So solute water potential and pressure potential add together. They're just purely additive to give the overall water potential of a particular cell, for example. So this is the equation that the IB has given you to learn. It's just two components of water potential that add together to give you the overall water potential. So we're going to deal first with solute potential. Before that, though, I'm just going to check in that there's no too many questions back in the chat, which there isn't. But any questions, hopefully, you reminder to my colleague Phil, who's behind the scenes. If you have any particular difficulty understanding any of the concepts or anything you want clarified, she'll be able to answer that in the Q&A section of the Zoom call. Okay. Okay. Captions to be enabled. Yes, I think that would seem fine. We'll do that. Thank you for that request. Now, solute water potential. We're going to talk about solvation. This is the way that water acts to dissolve other things. You'll know from previous subtopics that water is often known as the universal solvent. It's very, very good at dissolving other things. It's one of its important properties that makes it important for life. And there it is, H2O in its particular configuration. It has that sort of two sides of a triangle kind of shape. And it has a polar structure, which means that the oxygen atom is very slightly negatively charged compared to the hydrogen atoms, which are slightly positively charged. And that polarity is absolutely crucial to its function or to its functions as a supporter of life. It can form hydrogen bonds very easily with other polar molecules and surround other polar molecules and dissolve them. And so dissolving a molecule means to separate all of the solute molecules away from each other and surround each one with water. That's why when you put a spoonful of sugar into water, eventually the sugar disappears, or it looks like it's disappeared, because each individual sugar molecule is surrounded by water, and you can't see an individual molecule, they're just too small, as opposed to an individual crystal of sugar, which would have absolutely trillions and trillions of sugar molecules just in one crystal. Okay, it can form hydrogen bonds to itself, of course, and you know from the water subtopic that that's very important in explaining things like the high boiling point that water has, etc., and the fact that it can exist as liquid water on Earth. Okay, so there's some examples of water hydrogen bonding to other water molecules. Here's a solute particle. This could be a negatively charged ion like chloride. So chloride in sodium chloride, common salt. The chloride ion would be separated from all the other sodiums and chlorides in a piece of solid salt in a crystal and surrounded like this because the slight positive charge of the hydrogens would be attracted to the negative charge of the chloride ion that's given to it by its extra electron. And so that particular ion is dissolved and away from all the others. Similarly, a positive ion like the sodium, well, the water can arrange itself around the sodium in a different way, slightly different orientation. But what you get there is what we call a hydration shell. It's almost like a shell of water. I like to think of it as a sort of bodyguard of water that surrounds each dissolved ion in order to keep that ion separate from all the others. And that's the essence of a solution. Now, there will be plenty of other water molecules floating around here that are not associated with solutes, and they are what we call free water. And we'll talk about their involvement in water potential a bit later. So there's an example of a sodium chloride ion, or a pair of ions, being surrounded by their hydration shell. Now, the key point here is that all these water molecules, and we're showing 12 here, they are bound sort of almost joined at the hip, if you like. They're bound to their ion. They can't move about on their own. And so that affects the way that water behaves when it encounters membranes and situations where you've got different solute potentials either side of a different membrane. So these water molecules are doing their job. They're sticking to their ion and they're not dissolved. They're not moving around independently. We've got a little animation about that here. So imagine these are all water molecules. That it's not accurate in the sense that the water molecules in liquid form would be touching each other, but I wanted to moving around each other, but I wanted to show them moving around a little bit like this, okay? And they're just moving around at random. That will be in pure water. Now, if we were to introduce a solute molecule here, shown by this black molecule, what would happen is the free water molecules would move around as they already were doing before, but you'd get this hydration shell forming around the solute like that. And what you can see is that there are fewer water molecules now moving around freely. We'll grey out the dissolved ion there with its hydration shell, in the sense that that complex, if you like, is no longer free to move around. Well, it does move around, but it can't cross a membrane. So it moves around like that as in a solution, okay? This is important when it comes to situations where there's a membrane. So imagine here we've got a cellular system with the same water concentration either side of a partially permeable membrane. So this membrane is permeable to water, but not to certain solutes within the water. And so, sure enough, through random motion, water can diffuse either way. You know, it can go either way across the membrane. So you might have a situation where there might be slightly more water on one side, but that will be counteracted by random movement of water in the opposite direction. So essentially nothing happens, all right, in terms of the overall balance of water molecules either side. But if we bring in the solute molecule again, like we did before, we get the hydration shell forming like it did before, and we'll grey that out because essentially that now can't pass through the membrane. And what it means is that we have an imbalance of water molecules. We have 20 over on one side and only 14 free water molecules on the other. Well, what that means is that there's a statistically higher chance that water will pass from right to left than it will do from left to right. Water can still pass from left to right through random motion, but what eventually happens is you get this net movement of water such that eventually you'll have a relatively equal concentration of water on both sides, up to a point, okay? It's to do with the probability that water moves from right to left is greater than it would be from moving left to right. So eventually, water does move net from right to left, and what that would cause, and if we look at the membrane here, that would cause the membrane to actually bow out because there's more material now on the left hand. There are more atoms on the left hand side than there were before. And so this explains how membranes behave in different osmotic conditions, and it's very important in terms of how solute water potential affects cells and their ability to do their jobs. There are loads of different scenarios where osmosis like this can affect a cell either to its benefit or to its detriment. Okay. So what's the definition of solute water potential then? I would say it's the pressure exerted by water that moves into another area of pure, clear water. Now, at this point, guys, it's really important that I would encourage you to always, if you write about water potential in your answer, there's a tendency to leave out the word solute because that's often what we're referring to in a question that's about osmosis, or it might be about what happens to a cell under certain conditions. But don't forget, water potential is made up of solute and pressure. So in this case, we're almost always talking about solute water potential. Now, pure water will not move, so has a solute potential of 0. All right, pure water will not effectively move. It'll move in one direction in the same rate as in the other direction. So anything that's a solution that has solutes in it will have water diffusing into them by osmosis. So the water will be moving from pure water, not towards the pure water. Now, if we look at our definition here, where it says the pressure that moves into another area of pure water. Well, it's not moving into another area of pure water, is it? It's moving out of. We're going out of an area of pure water. So this is why we have solutions that have a negative solute potential, all right? It's a really important consideration. It seems clumsy to have a scale that tops out at 0 and that is all measured on a negative scale, but that's the reason for it, is that water will not move into pure water necessarily, not by osmosis anyway. It could move in by pressure effects. So the Greek letter psi or Psi is used. The Greek water god was Poseidon, which is kind of a bit like the letter Psi. And there he is. And he actually carried a trident, which has got the shape of the letter psi, which is entirely coincidental, I think. But it's a nice way to remember it if that helps. Okay, the letter psi. And as we said before, the symbol for solute water potential is psi subscript S. Okay, as has been mentioned in the chat, here's an opportunity for you to provide a little bit of feedback here, which is for after the session. So if you could scan that QR code on the left. Hopefully you've already got the Google response form, the middle QR code open for your answer to the upcoming questions. And that's the middle QR code. And the one on the right is the PDF notes for today's session, which, again, many of you will have open at this stage. Okay. Let me just quickly check the chat. Okay, just at this point, just on a 1 to 5 scale, if you could put in the webinar chat, 1 if you're not happy with the content so far. We're about to go into some questions. 5 is you're entirely happy. So I'm seeing 3s and 4s. Thank you. Much appreciated. Yeah, that's good. Thank you. Okay. We'll push on, and hopefully you're using the Q&A function as well, which we mentioned. I'll repeat about that for you to use as and when you you have a bit of conceptual information that's oh, Louise has raised a hand. I'm happy to take a question in the chat, Louise, if you want to write that, if it's a short question. Okay, just no, okay, that's fine. You can always, oh, okay, thanks, Louise, no problem. We'll move on. Glad you're with us. Okay. Now, this is something you can answer in the Google document. This is multi-choice question 1. Which cell of those 4, A, B, C, D, will have the highest likelihood of absorbing water by osmosis? Okay. It's just a straight A to D multi-choice question. Okay. I'm seeing some responses coming in now, which is good. And you can use the Google Sheet for that. If you, I wouldn't always be able to see your answers if you put them in the webinar chat. I am seeing some, yeah, I'm seeing some correct answers and some incorrect answers. Okay, I'm seeing all C's and D's at this point, which is good, because the answer is certainly one of those two. We'll go into the answer here and the reasons. Okay. The answer is water will always move from an area of high water potential to an area of low water potential. That's part of the definition of osmosis, isn't it? And because we're talking about a cell, we're talking about an actual cell here. So you can assume that it's bounded by a membrane. Well, it will be if it's a cell. The lowest water potential is the largest negative number on this list. It's D. Now, one thing that students surprisingly often have an issue with, and this may have affected you today, is that you've got to be careful to notice that these are actually minus signs. They're negative symbols. They're not bullet points or anything like that. So you've got to be able to read the whole number correctly. So the answer is D. Pay close attention to the signs of numbers, particularly in multi-choices. They're very small and very easy to miss, these signs. And of course, they're on a negative scale for the reasons that we've described in the previous question. Thank you for your responses. I'm seeing mainly correct answers for that question now, which is great to see. Okay. Second one. Let's see. Which sketch graph, there are 4 sketch graphs here, shows the relationship between the solute concentration, that's plotted on the horizontal axis, and the solute water potential. Okay, slightly more difficult question perhaps, but take a moment to put your responses in the Google document for that. Okay, seeing some responses here. Oops, sorry. Okay, I'm seeing A. Okay. Somebody's answered C. Okay. This one's a tougher question, actually. This would have a higher difficulty tariff. I'm going to reveal the answer here. The answer is actually B, in the sense that, let me explain. If we look at answer B, well, water potential, remember, is on a negative scale. So the x-axis would naturally be here at the top. This is the x-axis here, okay? And of course, these are all negative numbers. That might be minus 50 there. That might be minus 100, whatever the units are, okay? So the reason is it's a negative scale. So that's why the x-axis is on the top. And it's a directly proportional relationship between solute concentration and the solute water potential. So that there's it's a straight line graph. Okay. Okay, before we move on to the next one, just going to have a quick look at the webinar. Okay, good. Hope we're all doing well so far. We're going to move on now to a slightly longer question, which is uh, in the form of a structured question. This is a 3-mark question. And like any question, I would very strongly urge you, for reasons that we'll go into at some later stage, to very carefully look at the question. Firstly, identify the command word. Now, the command word is explain. So for that, you've got to know your biology. You've got to be able to explain a biological phenomenon, so to speak. Explain why the solute potential, okay, so that's the solute water potential of a cell contents, is always expressed as a negative number. So this relates to the question we just had, the multi-choice question we just had. And so just take a moment you can type this into your Google document, or you can just write it down for your own use. I'm going to take you through a sort of a model answer, if you like, or not a model answer, but a suggested mark scheme, and the way that you can address these 3 marks. The other thing, of course, to do is to very carefully take on board the number of marks that are required. You should do this for every question, because that will indicate to you it's done deliberately by the examiners, because they effectively want you to make 3 separate points, okay, that are credit-worthy in their own right. So you'll have to try and structure your knowledge of water potential, etc., or solute potential, into 3 separate points that lead to this an explanation of the negative scale. Okay, just have a couple of moments on that. I'm just going to see if there are some responses in the chat. Okay, now nothing in the chat, so that's good. I'm just going to look at the Google responses now. Yeah, there's a great response that's been put in here. Well done to that guy, who's a person who's put it in. The solute potential is a measure of the tendency of water to move into an area of pure clear water. Therefore, as if there is a cell, it has solutes inside, meaning the water moves away from pure clear water and towards the solutes. This gives the solute potential a negative value. That to me would be a model answer. Well done, whoever wrote that. 3 nicely structured points there. You've written it in bullet points, which is fine. As long as it's clearly written, etc., it doesn't matter whether you write in sentences or bullet points. I would always urge you to write in sentences, just from the point of view of bullet points sometimes cause you to be a little bit too succinct, too concise with your answer. Although that answer, as I read it out, isn't concise. It's beautifully structured, really nicely written. Well done. I'm just having a look at another one. Lois, reduce the free energy of water molecules, making psi more negative. Therefore, solutions always have negative water potential. Another terrific answer. Thank you to those of you who've put that answer in. Those would easily pass muster as a good answer. A mark scheme might look a bit like this. Potential is the tendency of water to move into an area of pure water. It will not move. These are just other ways you can say the same thing. This is a mark scheme that an examiner might use for it. It will move away from an area or out of high water concentration. The cell always has some solutes or dissolved substances in it. It wouldn't be a cell if it didn't, okay? It would just be a bag of pure water, which would be lifeless. So water will move or diffuse into that cell from an area of pure water, exerting negative pressure within the cell, okay? Here's a sample answer. Solute potential is a tendency. So that's the point that one of our contributors made on the Google Doc. In osmosis, we observe that water always diffuses from an area of high into a more hypertonic area. Here I've used the keyword. So using a keyword like that's a keyword because it's mentioned in the IB spec, is sometimes a smart thing to do, in the sense that if you've used it correctly, which the chances are you will use it correctly if you know what it means, it could well be something that appears in the mark scheme. So the examiner would have no option but to give you a tick for that. Yeah, the reverse of moving into pure water, which has a solute potential of 0. So a negative solute water potential is exerted. This allows water to move across the partially permeable membrane. That last sentence isn't strictly necessary, but it gives a bit of context, it gives the examiner a bit of reassurance that you're actually thinking about a cell in a biological system as opposed to just water and a membrane in some kind of inorganic laboratory setup, that sort of thing. Very nice answers on the Google Docs. Thank you very much for those. I really appreciate that. Here's another structured question that might come up on this. So in the same way, I would always ask you rigorously to do this with every question. First of all, what are the command words? Compare and contrast. Okay, so for that, compare and contrast means give some similarities and some differences, okay, between solute water potential and pressure potential within a plant cell. Now, plant cells important because any answers that relate to animal cells or specifically relate to animal cells might not gain credit. So it's similarities and differences. And again, 4 marks. So there's quite a bit to write here. So I would say 4 sentences on that. Maybe one thing that's the same, one comparison, and 3 contrasting points, or 2 and 2, whichever you feel is more appropriate to the scenario. Here I would say, yeah, well, 1 and 3 or 2 and 2, but certainly don't write 4 differences because then that wouldn't give you access to all the 4 marks. Very honest response there. Haven't got a clue, honestly, so excited to learn this one. Well, that's great that you say so. Again, I appreciate when we get the feedback like that from our viewers because these are important questions that will help you move that middling score that you were at the beginning up to something higher. So yeah, I will dive into an answer for this now rather than look at some more answers because we do have quite a bit to get through and I want to keep the momentum going. So let's have a look at this one. Right, well, similarities. Well, both of these aspects of water potential, they cause water to move. And they cause pressure forces. So if you draw a comparison between the two, you could say either of those two as being a similarity. Differences wise, well, you've got the idea that solute water potential is a negative pressure, whilst pressure is a positive force. So the pressure potential inside a cell is usually on a positive scale when that cell is exerting pressure on its cell membrane, or if it's a plant cell, pushing its cell membrane up against its cell wall to give the cell that turgidity that often plant cells require to be healthy or to support themselves. You could say also that solute is a function of what dissolved substances are in that part of the cell, whereas pressure is just caused by mechanical or physical forces on the cell that might be caused by, a different structure or organ within an organism. Solute water potential effectively causes a pull of water. Pressure potential causes a push force on water. That's quite an obscure one, but I think it would gain some credit if you were to put that in an exam answer. Yeah, somebody's put that in the Google Doc, which is terrific. You can present. This is an idea for you to do. You could write your answer as longhand, but one thing that we try and do in our question bank questions sometimes is present the answer as a table, which may seem a bit weird, a bit strange to you, but it works quite well with similarities and difference with compare and contrast questions. And you could almost write a table like this. So the way this one's been done is that we've put the similarity or the compare down here at the bottom, and that both are measured in pressure units of kilopascals, which they are, which lines up with this mark scheme point here. And the remainder are all differences. They're all contrasting points, aren't they? So you can put the cause of solute potential is solute concentration and physical pressure, and you get a mark for making a statement that contrasts those two. The value is always negative. Pressure potential can be positive, negative, or 0. Okay, or if you were to just say it's positive, you'd probably get a mark because it does most generally in biological systems. Pressure potential is a positive force. Purpose is to pull water by osmosis, and that pushes, and it's affected by concentration types of solutes, turgor pressure or compression. And it's absolutely okay to write your answer as a table like that. In fact, I've been an examiner before, and on the very rare occasions that I saw an answer written like this, it was almost always full marks. I'm not saying that making it as a table will guarantee you full marks, but it organizes your thoughts really well, I think, to enable you to draw important contrasts between these two things, these two types of water potential, and to also, like in this merge cell at the bottom here, give the similarities, the two things that are sort of a feature that is the same about the two types of potential. It really is okay to do your answer like that, and the examiners will probably love you for it. So a little hint, don't always do your answers as tables. It doesn't guarantee you high marks, but it's something that I think would, it helps to marshal your thoughts and get them down on paper in a concise way. Remember, with a compare and contrast question, it's really important to include at least one similarity and one difference. If the command word didn't have the word compare in, for example, and you were just being asked to do a contrast between two parameters, then you don't have to write anything that's similar. But in this case, you do. So you would only get a maximum of 3 marks, maybe, or maybe 2, depending on how the mark scheme's written, if you only include contrasting points. Right then, the other part of water potential, and having dealt with solute potential, is pressure potential, which is this psi underscore P. Okay, it's hopefully slightly more easy to understand. It's the energy exerted by water particles on the surroundings when under pressure. That's essentially a sort of pseudo-physics type of explanation about it. So in our biological setting, and most of these, the spec does concentrate more on plant cells than it does on animal cells in this topic, because animal cells do tend to, they don't have the physical protection afforded by a cell wall. So an animal cell, if it's exposed to a highly hypertonic environment, will probably lyse through osmosis and break apart, which isn't conducive to life. Whereas a plant cell has got more protection against pressure, and it relies upon turgor pressure, for example, for a flower stem to remain upright, to stop the plant from wilting, so that it can present its leaves to the sun for photosynthesis more effectively. So in a biological setting, how does pressure potential work? Well, it's the pressure exerted by the cell's liquid contents, which is cytoplasm and any vacuole contents on the inside of the cell. And it acts a bit like this. It's acting on the cell membrane, which pushes against the cell membrane, is this little black line around the edge, and the cell wall is this thicker green layer, which is the structural support made from cellulose most often. And the cell wall has the strength. It has the strength to withstand the pressure. Remember your lessons about the fibrous structure of cellulose and the strength it gives for cell walls. So again, we have the abbreviation psi underscore P for pressure potential. And the units are either kilopascals or megapascals, kilo being 1,000 newtons per square meter, or mega being 1,000,000 newtons per square meter. Megapascals or kilopascals. Always make sure you're aware of the units if you're answering a numerical based question. And it's usually positive in a healthy, well-hydrated cell in a hypertonic environment. So the hypertonic environment would mean there's a higher water solute potential outside the cell, which would cause water to move into that cell by osmosis, which in turn pushes the cell membrane out towards the cell wall. And that's a condition called cell turgor. It's a condition that most plant cells like to be in, because it gives structural support. It makes sure that the plant is well hydrated, and it allows even though the pressures, the potentials are not actually in balance, it means that there's an essence, there's a sense of stability there. The plant cell can stay stable in its environment and perform its function. If it's the stem of a flower, for example, a cell within that, its job is to hold the flower up, isn't it? And so it needs to be turgid to be able to do that. Multi-choice question 3. What is the solute potential of a palisade mesophyll cell whose overall water potential is negative 852 kilopascals per litre and whose pressure potential is 554 kilopascals per litre? Okay, so again, our magic highlighter. I'm not saying literally use a highlighter on everything, but I'm using this highlighter to try and draw your attention to what it's asking for. Solute potential. It's a palisade mesophyll cell, so that's an important photosynthetic cell in a leaf, isn't it? It's the main cell that performs the job of photosynthesis, making food, whose overall water potential is minus 852 and whose pressure potential is 554. Okay, so let's see what the answer will be. Seeing some responses here. Let me just see if there's any in the chat. I'm seeing all manner of responses, actually. So in a sense, I'm quite happy with this question in the sense that it's providing a bit of controversy. We'll go through the answer. We need the water potential equation for this, which is the overall water potential. Psi W is the solute water potential, psi underscore S, plus the pressure potential. Now, we're given some data in the question, aren't we, about that, where we substitute the values from the question into this equation. So the overall water potential is minus 852. That's this one. And the solute potential is what we're being asked to calculate. So we've got an equation, like any maths equation, we subtract 554 from each side to give us our response, which is A. Okay. All of you got that right on the Google Doc, but quite a few putting your answers in the chat missed out on that. Okay. Let's have a look at the chat. Okay. So that's the reason that one is, you have to do a little bit of maths here. And of course, you'll always have your calculators, won't you, to be able to do that. So it's negative 1406. The same warning applies here about negative signs. Make sure that you spot the difference between A and D, which is just a simple small negative sign, which you can very, very easily miss. Okay. A positive number won't always have a positive sign in front of it. So it depends how the exam is written. And it's perfectly normal to assume that a number is positive if it doesn't have a positive sign in front of it. Right, this question now is a slightly different, I'm taking a different tack with this question, guys, because you've been answering quite a few questions of mine, and I'm really grateful to the responses you've given, which has been great. This time, though, what I want you to do is to look at this answer that another student wrote, and in the sense that a lot of you are in those middling grades, you rated your knowledge of this subject before today's session at a kind of 5 or 6 or 7. This answer I'm going to put in front of you in a moment is probably the kind of answer that a student like you might well have written, okay? It's not a complete disaster. It's not a 0 score, but neither is it a perfect answer either. It's got some good things in it and some bad things, which is very, very typical of the student who really wants to improve their answer. So I'm going to put this answer up for you, and for you to then just have a few minutes to think about the kind of critique. Imagine that your best friend who's sitting in class with you had written this answer and has asked you to mark their answer. Okay, think of it like that if you like. So let's go through the question with the highlighter again. Describe is the command word. Okay, so we don't have to do any explanation there. The effects on a plant cell of changes in water potential. Now, there's quite a bit to talk about there, isn't there? Okay, so there's 4 marks. Maybe 4 separate effects here. Changes in water potential. We don't know whether it's changes in a negative or positive direction, but we don't have to explain them. We don't have to go into long, detailed explanations. We just, a describe question requires you to say what you see, okay? So I'm going to put this answer up on the screen for you now, guys. Have a read of that I'm just going to give it about a minute of me not talking. And then if in that time, if you can put some of your comments into the Google document for this one, okay? If there's a space for it. Yeah, I've put the actual answer in, I've put the student's answer in the Google document. So you can see it on your screen. You can also see it in the Google document. Let's just have a minute to think about how you would critique that answer. So highlight the good things, what somebody has said that's worth a mark maybe, and the things that are maybe not so great about that answer. Okay, I'll be quiet for a minute. Okay, hope I haven't seen any responses in the Google Doc. Let me just have a quick look in the chat to see if there's any. Okay. Right. We'll go through this anyway. Some of the things about this question that may or may not be better. A plant cell will fill by water diffusion. Well, there's a better term for that, isn't there? Okay. I would say osmosis is a better term. Okay. It's not going to lose you a mark because it's strictly correct what's been written, but osmosis is a better term because osmosis, remember, is a form of diffusion that relates to water across a membrane. So it's a slightly better term. So a plant cell will fill by water osmosis. Well, I mean, I've got a slight issue with the idea of a plant cell will fill. Okay. Somebody's made that point in the Google response, by the way, because it might be fairly full already. And it's the word fill is a bit of a vague term there. But again, it's not enough to cause a problem, really. When the water potential outside the cell is higher than outside, okay? A plant cell will become flaccid, okay, when the water potential inside the cell is higher than outside the cell. Yeah, I think that's okay. That's a good mark, and it's a description, isn't it? It's a description. It hasn't necessarily explained why that happens, but it's described what will happen. So I like number 2. This here, somebody's made this in the Google. This is going to be completely ignored by an examiner because it wants you to talk about a plant cell. Referencing human cells in this way is not going to earn any marks at all, even though what this person has written about a red blood cell will become crenated when the water potential inside is higher than outside the cell. Well, that's true. It's actually true, but it bears no relation to what's being asked in the question. It's a very common error that students make. They sometimes trip up and start writing everything they know about water potential and the effect on cells without having really noticed that this question only wants answers about plants. It's good to see somebody's made that point in the Google Doc. Thank you for that. A turgid cell has, a turgid cell has water potential and pressure potential in balance, so it will remain in a stable state. Well, that's not entirely true either, in the sense that there is a state of balance in the cell, but it doesn't mean that the solute potential and the pressure potential are, that could be plus 300, sorry, minus 300, say, and the pressure potential wouldn't be plus 300. It would probably be plus 150 or something like that. So they're not exactly in balance, but the state that the cell is in a stable state. So I'm a bit dubious about that. Plant cells can change their behavior by deliberately manipulating solute water potential using active transport of mineral ions. Well, yes, that is relevant because it's an effect of changes in water potential. There's got to be a reason for all this water movement. And so, for example, the way that a plant cell, like a stomatal guard cell, it actively transports mineral ions into and out of itself, so that lowers the solute water potential in the cell, and the cell can fill up with water by osmosis. So it moves ions around actively, and water follows by osmosis. So that's a deliberate ploy by the cell to change the shape of a guard cell, which of course determines whether the stoma, is open or closed. So again, that's a relevant point. Now, I'd really encourage you to do this kind of work with, if you study in groups and there's some time before the exam, if you study in pairs or groups, get together with your buddy, and it doesn't have to be somebody who's even your closest friend. It could be somebody that you work well with, and you can critique and pick apart each other's answers and improve them in this way. It's a really powerful technique. And if you can't do it with another person, you can easily do it using published resources like our very own at Revision Village, or you can use the examiner mark schemes, although they're a little bit more difficult to interpret from past papers. Little plug for Revision Village here. We write mark schemes and sample answers that we think students will, of the kind that we think students can write too. So when you read them, it's something that you can relate to and go, oh yeah, that makes sense now. All right. Very powerful technique, writing your answer out and then improving it with some external help, whether it's from a friend or from a well-written revision resource like ours. So cell turgor, we've seen what happens with cell turgor. We can see this is the bit in the specification at the end of the specification that says how cells are affected. We're going to mainly concentrate on plant cells, as we said before, in the sense that water potential affects cells through affording cell turgor like this, so making the cell nice and filled out and, performing its structural role really well. This would occur in a hypertonic environment, which in most cases is the case because cells and plants tend to concentrate the solutes within the cells. So the external water, which is usually, if you're talking about a land plant, a terrestrial plant, the external source would be soil water, which would be hypotonic because soil water is essentially quite pure water with a high solute potential and a low solute concentration. In a hypertonic environment, you get this effect where the water flowing out of the cell by osmosis exceeds the water flowing in by osmosis. And we call that plasmolysis, and it causes the cell membrane to detach partially from the cell wall, because quite frankly, the cell membrane is containing less fluid in it than it did before. So that cell membrane has to indent itself, if you like, to stay, to stay in contact with all the cytoplasm. And that would happen in a hypertonic environment. It's called plasmolysis. It would weaken the cell wall because if you imagine the cell wall being a rigid cellulose box, and the cytoplasm, imagine that as like a balloon filled with water. The balloon inside the rigid box would strengthen the box if the balloon is touching the sides and pushing against the sides of the box. Here, the water balloon, which is meant to represent the cytoplasm isn't touching the sides of the cell wall. So it fundamentally weakens the cell wall, and it can cause wilting, amongst other things, in the early stages of a plant being in a hypertonic environment or being dehydrated, not watered enough. And the term flaccid we use for what we call an isotonic environment, where a cell it's kind of doing all right. It's got enough water. There's water flowing into it and out of it at approximately the same rate. The cell is happy doing its job, but it's not completely turgid. It's not completely full of water as it would be in the turgid situation. So the cell water content depends on how long the surroundings have been isotonic for and other factors. So the stable environment of a cell can affect whether the changing environment of a cell, sorry, can affect whether the cells move between plasmolysis, flaccidity, turgidity, and back again. Okay, and it does vary a lot during the course of a day, for example. Okay, here's another multi-choice question, number 4. Which row of the table, so this is just a case of ABCD, gives the most likely combination? All right, so you're having to sort of use a bit of common sense here, because the most likely combination, you don't know we don't necessarily know what the water potential values are in a system, do we? So we're asked to give the most likely combination of solute water potential and pressure potential for a fully functional spongy mesophyll cell in a healthy terrestrial plant. So again, we're just looking for a spongy mesophyll cell, which is part of the leaf, of course, that creates that air gap for gas exchange. So you would expect that cell to be, nicely turgid, etc., and well supplied with water through the xylem vessels, etc. Healthy terrestrial plant, so it's probably photosynthesizing away quite nicely, and it has these various values. Okay, so let's have a look at the responses that we're getting here. We're getting some variety of responses, which again is good to see. Okay, I'm seeing B's, D's, couple of A's. Okay, let's reveal the answer here. It's D. Okay. The reason it's D, it's that solute potentials are always scored on a negative scale. So if we just go back to the numbers, we can always eliminate anything that's not a solute potential on a negative scale. Okay. Now, we can eliminate A because this is a real cell. It's in an actual plant. It's not going to have a water potential of 0. It's not going to be full of pure water. And it's not going to have a positive solute potential either, because that doesn't exist. There's no such thing as a positive solute potential. So we've immediately eliminated A and C from our possible answers, before we've even looked at pressure potential. Now, pressure potential-wise, so we've eliminated these two. We've either got a negative or a positive value. Well, I'm liking more the positive value because it's a fully functional, healthy terrestrial plant. The cell contents, the cytoplasm and vacuole, are going to be pushing up against the cell wall. That's going to be putting a pressure on the inside of the cell wall. So if you could measure the pressure inside that cell, it would have a positive value. So our only two combination of negative and positive is, by definition, answer D. So that's the kind of thought process that I want you to put into these sorts of questions. And when you're doing a multi-choice question, you can almost always eliminate one or two answers that are obviously wrong. And for that, we would say, well, you can't have a solute potential of 0 inside a cell. It doesn't exist. It's impossible. It wouldn't be a cell then, would it? So you can eliminate A and C. And then you might have a third answer, in this case B, that could be plausible. So you could look at the answer, the pressure potential, and go, would it be a negative pressure potential? That would have to be losing water, wouldn't it? Oh, that can't be the case, because and you go back to the question and you read that it's a healthy terrestrial plant, and and everything's peachy in terms of that cell and how it's surviving. So it's not going to be losing water. So it's going to have a positive pressure potential. So it's a sequential way to try and address those sorts of points. As a way of now zeroing in on the correct answer. Now this question here is kind of we're getting to the end now, and I just wanted to throw this question at you, which you may think is a little bit strange, okay? And the reason I would like you to bear with me on this. Actually, it's not actually anything to do with water potential, shock horror, but this is something that I believe you can actually benefit from greatly by bearing with me on this particular exercise. Go into the web chat on the Zoom for this one. There isn't a space on the Google Doc for it. But what I'd like you to do is just very, very simply answer this question. And the question is, where you are, what time is it? Okay. Now I'll give you a clue from here. I'm in the UK. It's 1:07 p.m. here. Okay. 1:07 p.m. So I just want you now in the Zoom chat to bob your answer into there. Okay, I'm getting lots of 07s. Of course, the times all vary. You're all in different time zones. Okay, and everybody's giving me 07 answers, which is tremendous. Okay, people are actually also giving me their locations, which is great. Kazakhstan, that's fantastic. Switzerland, Bahamas, Jordan, Switzerland. This is really an international IB, isn't it? Everybody's answering the question with a time here. Now, what would you think if somebody said in their answer in the question, they're answering the question, where are you, what time is it? And somebody types in, it's Thursday, the 17th of April. All right. Somebody could type that in. Why don't somebody just type that in for me? Okay. Just type that in. I'm not going to make an example of you. But somebody could easily answer that. And you might be thinking, well, hang on, that's not the question that I asked you, is it? Because I asked you the time and somebody's answering with the date. And that will be a very strange conversation. You know, I'd say to you, no, I know the date. I'm asking you what time it is. Now, why is this a bit related to biology? Well, it's related to all of answering, the whole art of answering exam questions, because believe it or not, students do this all the time. They answer the wrong question. And the examiners look at the answer and they think the answer is all about, the question might be like the example we saw earlier, where the question was about a plant cell. Now, there'll be students who write all they know about animal cells and how they would behave and and be wasting time. All right. It's a natural tendency in an exam to want to get on with it, to want to write your answers down and move on to the next question. But you have to take the time to digest the question first and really get it clear in your head. What is this question asking me to write about? And the question I asked you just now was, what's the time? And you've all answered with the time, which is great. Okay. But if somebody had answered with the date, it would still be correct because today's date is the 17th of April. Okay. And it even is in somewhere like Auckland, it might actually be tomorrow in Auckland now, but never mind. The point is that students very often answer the question that they think they see. All right. Advice is always to answer the question that you literally get your pen, like my pen here, and put it on the table where you can't touch it, and then spend some time looking at the question. What a lot of people do in exams, and this is something I would recommend, get one of these, highlight a pen, and just highlight the relevant points of the question, the command word, the number of marks, the restrictive sentences in the question that, for example, talk about a plant cell. It doesn't want you to talk about an animal cell. And you will gain so much time from that that you'll be thinking, I'm so glad I took some time to look at the question. This is a general exam tip that applies to any question. All right, it's not just questions about water potential. But having done examining and been an examiner and been a teacher, I've seen so many students, and there's several of you in this room today that will probably do the same thing. Obviously, I don't know any of you, but it's a very common thing that students do. Make sure that you really think about where your answer is going. And that's my sort of parting gesture, parting shot really for today. We do encourage you, though, to use our other resources. We hope this has helped, and I've been really happy. You've been answering some questions really well, and I really appreciate that using the chat. My colleague Phil is going to brief me at the end about the Q&A session that went on, but I imagine that was very lively as well. So again, thank you to anyone who's used that. In terms of Revision Village, the way we help, we have many other resources. They're all linked here. We have past paper questions with video explanations. So we have one of our qualified teacher examiners explaining why the answer is the answer, particularly in the case of multi-choice, why the wrong answers are wrong. And that's very valuable too. We have a question bank that we write with on questions that are purely narrow focused on the IB, and it says clearly whether it's standard level or high level. Key concept videos that summarize topics when you're short of time. And so there's lots of ways that we can help you further, and it's almost always a worthwhile investment in your learning to engage with Revision Village in that way, and we'd be very happy to see you back. Thank you so much for your time and attendance today. It's been good. I've been really happy with the level of engagement that you've had. It's very difficult sort of teaching into a large Zoom group like this, but the level of interaction you've provided has been terrific, and I thank you for it. And I'm sure if there's any other questions, there's ways you can reach out. Put some more. We'll keep the chat open for a while. Okay, thank you. Oh, I'm getting some great feedback about Phil on the question and answer, which is terrific. Thank you. Being a pretty niche topic. Thank you for that person who's taken time to give the feedback. And yeah, hope it's been useful for you. Thank you very much indeed. And we'll hope to see you again.